Every morning, you expect the exact same result, a single, thick drop that yields a rich, instant lather. That consistency is an engineered illusion. What you perceive as a simple liquid is actually a volatile chemical matrix. The primary ingredients, surfactants, oils, and water, naturally repel one another and actively want to separate. Forcing these opposing elements into a smooth, skin-safe state requires a gauntlet of high-pressure mechanical engineering. To maintain this stability at scale, the process moves into facilities that look more like oil refineries. These storage tanks house the raw chemical ingredients in pharmaceutical-grade conditions. Your daily routine is the endpoint of thousands of gallons of chemical interaction, stabilized by industrial force. The process begins inside blending reactors, where thousands of gallons of primary and secondary surfactants are combined into a single mixture. This diagram shows a surfactant. It is an amphiphilic molecule, consisting of a hydrophilic head that attracts water and a hydrophobic tail that attracts oil. When introduced to oils on your scalp, these molecules cluster together, orienting their tails inward to surround the oil. This spherical structure, a micelle, allows the debris to be washed away by water in your shower. Maintaining this micellar matrix across a large-scale batch requires high-shear mixing blades. These rotors relentlessly knead the ingredients to force the raw materials into a single unified mass. Blending shampoo is a physical binding process, using mechanical energy to connect chemical structures that are fundamentally opposed. After mixing, the fluid is pushed through high-pressure homogenizing valves to break down any remaining ingredient clumps before entering the evaluation phase. The exact thickness of the fluid is measured using a Brookfield viscometer. This test ensures the tactile glide of the liquid meets the manufacturer's exact specifications. Lather potential is also mathematically quantified. Using a Ross-Miles foam column test, chemists measure the precise height and stability of the foam generated by the batch. The standards are exacting. If the pH balance or the foam stability deviates by even 0.1%, the batch is flagged for adjustment or disposal. Subjective human experiences, like the feeling of a rich lather, are reduced to scientific measurements to ensure every bottle is identical. The filling line is the most delicate phase of the production journey. Rows of empty bottles move along a conveyor to receive the fluid. Injecting a thick liquid at high speed requires precise pneumatic pressure. These metallic nozzles are thermodynamically controlled to maintain a specific flow rate. The liquid must form an unbroken stream. If the flow is interrupted, air bubbles become trapped, destroying the liquid's surface tension and texture. Through this mechanical precision, a massive chemical batch is captured into millions of perfectly stabilized individual products. Caps and labels are applied at high speeds to create an airtight seal. This prevents chemical degradation and locks in the volatile fragrance compounds. Preserving the chemical matrix is only part of the engineering challenge. These towering bales of plastic waste represent the environmental pressure now forcing a redesign of the bottle itself. To lower carbon emissions and reduce reliance on virgin materials, the industry is transitioning to post-consumer recycled plastics, such as PCR PET and PCR HDPE. New regulations are shifting production toward monomaterial packaging. Conventional bottles often use multiple plastic types, causing rejection at sorting facilities. A monomaterial design uses a single plastic type for the bottle, cap, and pump, allowing it to flow successfully into the recycling stream. The challenge for the factory is to redesign the physical vessel to meet these mandates while keeping the volatile liquid inside perfectly stable. In the final stage of the journey, synchronized automation takes over. Robotic arms precisely palletize the boxes for global distribution. Despite this reliance on robotics, the final check is human. Master chemists sample the product to test the tactile glide and fragrance release of the final batch. A single production line can fill, cap, and label hundreds of bottles every 60 seconds, maintaining a uniform chemical profile across every unit. Washing your hair is the final stage of a process that begins in stainless steel reactors and ends with robotic distribution. Every bottle is a stabilized chemical matrix held together by industrial force.